Now, let us take a numerical example about charging and discharging of capacitors. To make a sense of the problem, let us make this problem or this example a real physical problem. As a real physical problem, if you have a car which rolls along the pavement, there is some electrons moves from the pavement first into the tire and then into the car body. The car stores this excessive charge and the associated electric potential energy as if the car body were one plate of capacitor and the pavement will be the other plate. So effectively, there is some charge moving through the tire to the body of the car, and the body of the car, which is conducting material, plays the role of the upper plate, and the earth play the role of the lower plate. So between the body of the car and the ground, there is a capacitance. The car stores its excessive charge and the associated electric potential energy as if the car body were one plate of a capacitor and the pavement was the other plate. When the car stops, it discharges its excess charge and energy through the tires. So once the car stops, I have extra charge here and I have resistance here. So effectively the charge will move back to the ground through the tire. So it is like it's a charging capacitor. So while the car was moving, it was like charging capacitor, and once the car stops, there is no excess in electrons anymore. So the capacitor will discharge its extra charge. When the car stops, it discharges its excessive charge energy through the tire, just as the capacitor can discharge through a resistor. If there is a conducting object come within a few centimeters of the car before the car is discharged, the remaining energy can suddenly transfer to spark between the car and the object. So it is required to determine how long it will take to discharge this energy to be in the safe side. And actually, this is a situation when you comes in gas station and he asks you to stop mobile phone and everything electrically to avoid any electrostatic charge to make a spark. Okay? So when the car stopped at time t equals 0, the car ground potential was about 30 kilovolts, 30,000 volts. The car ground capacitance was 500 picofarad. And the resistance of each tire, we have 4 tires, the resistance of each tire is 100 gigaohm. The question is, how much time does the car take to discharge through the tire to drop below the critical value of the energy which corresponds U fire? Actually, if I have a charged capacitor, I have internal energy stored in the capacitor. So I want this internal energy to be reduced below the value of U fire. Where U fire, the spark will not inject the foil and cause fire if the peak energy of the spark energy is less than the critical value 50 millijoule. So first of all, it is required to find out the stored energy in this capacitor system, the initial stored energy. If the initial stored energy is below 50 millijoules, it's okay. It will not fire or not make a spark. But if it exceeds this 50 millijoules, what time will take to discharge this value through these resistances, which is mid giga ohms, to be less than 50 millijoule. So this is the question. If we are going to take it as equivalent circuit, so the equivalent circuit of the car or the body of the car is a capacitor, and the value of the capacitance is 500 picofarad, and this capacitor is already charged with a voltage 30 kilovolts. Now this capacitor will discharge across resistances of the tire. Each tire is 100 giga ohm, and effectively the tires play the role of barrier resistance. Why barrier resistance? Because if we assume that this is terminal 1 of the tire and this terminal 2 of the tire, the other tire, this terminal 1 and this terminal 2. Terminal 1 is connected to the body of the car and terminal 2 is connected to the ground. So both these two resistances, terminal 1 is connected to the same node and terminal 2 is connected to the same node, so they are in parallel. Similarly, the other two tires. So effectively, we have four parallel resistances which correspond to the four tires. So the problem now is that this capacitor will discharge in these four resistances. Before going in four resistance, we can take the equivalent resistance of these four parallel resistances. So we will take the equivalent resistance of the tires, and we have the body of the car, which is the capacitor, and the equivalent resistance of the four tires, which is these four resistances in parallel. And we will see, we will start, what is the energy inside the capacitor? Is it larger than the fire energy or not? If it is larger, how this energy would be discharged in the resistance, and when it will reach below the value of this U5. Okay, let us do this. The spark will not ignite the foil and cause fire if the spark energy is less than U5 50 millijoule. This is our target. Here we have the capacitor, we have four parallel resistances which correspond to the tire. We can say that the equivalent resistance are 1 over R equals 1 over R tire plus 1 over R tire plus 1 over R tire plus 1 over R tire, the four resistances. So effectively the equivalent resistance is R tire over 4, and the tire resistance is 100 giga ohms. So 100 giga means 10 to the power 9 over 4, so it means that 25 giga ohms. Now we have R, and already we have C, 500 picofarad. Okay, the energy. The energy in a charged capacitor equals Q squared over 2C. And if the capacitor is discharging in a resistor, the instantaneous value of the charge on the capacitor would be Q naught multiplied by e to the power minus t over RC. It is discharging value. So Q squared over 2C can be replaced as Q naught multiplied by e to the power minus t over RC squared over 2C. This is the instantaneous stored energy in this capacitor while it is discharging. Okay? Okay. So we can simplify this Q naught squared over 2C multiplied by e to the power minus 2t r over c. The square here can be just multiplication in the exponential term. And actually we know that the relation between Q and C is that Q equals C multiplied by V. So Q naught equal C multiplied by V naught, and C is 500 picofarad and V naught is 30 kilovolts. So we can say that the energy at any time equals CV naught squared over 2C. CV naught squared is Q naught squared over 2C multiplied by e to the power minus t over RC. Okay, this is C squared and here C, so we can say is half C multiplied by V naught squared multiplied by e to the power minus t over RC. Actually, half C multiplied by V naught squared is another form for U. Okay, alright. Okay, so if this the stored energy or the energy as a function of time, we can say that e to the power minus trc equal the reciprocal of this argument 2 over c multiplied by v naught squared multiplied by u. So we want to find the time. To find out the time, let us take the natural logarithm for both sides. So the natural logarithm for this term is minus 2t over rc, and here ln 2u over c v naught squared. Okay, so we can say that t equals minus rc over 2 ln 2u over c v naught squared. Now we want u to be at least or maximum, sorry, we need u maximum 50 millijoule. So this is the energy. And C is the capacitance, V is the initial voltage, V naught, and R and C. R is the equivalent resistance of the 4 tires, and C is 500 picofarad. So by replacing all this stuff, we find out the time required to discharge the capacitor to be in the safe side is minus R multiplied by C, R 25 giga ohms multiplied by C 500 picofarad. Pico means 10 to the power minus 12 over 2 multiplied by ln 2 the maximum value of U 50 millijoule, milli 10 to the power minus 3 over C 500 picofarad multiplied by V naught 30 kilovolt, 30 multiplied by 10 to the power 3, and the volt is squared, so this is squared. We calculate this stuff, we can find out the required time to be below the firing energy is 9.4 seconds. Okay,